Now that we've established some nice identities to solve and simplify block diagrams and feedback loops, we can take a look at a specific example just to see how this plays out. So let's go back to our simple spring mass damper. So we start with our system dynamics. That's our differential equation. From that, what we've done in the past weeks is we've produced an open loop transfer function that represents how the output is related to the input to that system, that forcing input U. And so now what happens is that U is actually created by our controller K. And that controller K uses this feedback employed to do the control. So we could decide to do it like we did in the the very first video from this class, which is to kind of write down all the signals and do some substitution to get you there. But you can also use some of the identities that we just introduced to help make this a lot easier. So what we're going to do is we're going to notice that this block, because there's nothing on this wire, we can kind of think about this block as being a 1 down here, because in the identities that we saw, we actually had a transfer function down there. So what we can do is we can reduce this down to R coming in to, just to be particularly clear, and then we're going to combine these two transfer functions together. And we combine two transfer functions in series like that just as K times G. So the new way to write this would be to say that we have a transfer function that looks, or sorry, a feedback diagram that looks like this, where our new transfer function in the top line is just K times G. And that's just combining these two blocks together. Now we're going to use our identity that allows us to simplify the feedback diagram part of this. And that says that the transfer function, so now we're going to convert this into something where we just have the reference going in to a block, and what comes out is Y. So now think about just essentially creating a collapsed version of that, and the transfer function that represents that is the top line kg over 1 plus kg again. And that's again because we have this unit feedback right here. All right, so now that we know what G is, we can also ask ourselves what is K, and so that's ultimately what we get to design. Either we would be specified, we would guess or be given a value transfer function for K, or we could design it. So we'll do both in this class. But in principle, we can plug in, we know that we can plug in G, which is this transfer function here. And so that just means if we leave K to be general, that's just some K of S, then we get this expression where we've just substituted in G in both of these spots. Notice what we're going to see, I didn't do this in the slide automatically, but pretty much every single time we get to this point, we're going to do the same kind of simplification, which is to notice that we can multiply the numerator and denominator by this expression here. And what's useful about noting is that this is where the poles of G reside. So these are the poles of the actual system. And if K had poles that it was going to introduce, those could also be in there too. But this is where the poles of G reside. And so now what we're going to do is we're going to be multiplying that characteristic equation top and bottom. And what that's going to do is going to just leave us with K on the numerator. And then we're going to rewrite the characteristic equation, ms squared plus bs plus c plus K. So this pattern of getting the open loop transfer function, forming the closed loop transfer function, plugging those in, and then doing this multiplication on top and bottom to clear that characteristic equation, that's going to happen over and over and over again. We're going to practice that a lot. But anyway, that is ultimately, this is the closed loop transfer function expression. This is how we plug in the open loop transfer function. And if we wanted to simplify it a little bit, that would be the way to do that.